In this episode of Building Blocks of Bharat, we explore the niche area where architecture and astronomy meet. As expected, our key focus will be the stunning Jantar Mantar of Jaipur. But if we look back, the study of astronomy and astrophysics in India dates back to the first millennium BCE, with famous astronomers and mathematicians who laid the foundations of this field. These include Aryabhat, Brahmagupta and Bhaskar. Between the 1st century BCE and the 17th century CE, great advances were made in the study of celestial objects, with the invention of the astronomical measurement instruments. But the real revolution in terms of accuracy of instrumentation and what can be called a leap in the science of astronomy was during the time of Maharaja Savai Jai Singh II, ruler of the Kingdom of Amer, or the state of Rajasthan as it is known today, which is where we are heading. In these, he has adapted and added to the designs of earlier site-based observatories to create a unique architecture for astronomical measurement, which was unprecedented in those times and is considered unequaled even today. Before exploring these instruments in detail, let us take a quick look at the prevalent astronomical theories of the time. The belief that the Earth lay at the center of the universe with the planets circling it was threatened in the 16th century by Nicholas Copernicus. His theory that the Sun lay at the center of the universe has been described as revolutionary, and it was. It challenged the age-long views of the way the universe worked and the importance of the Earth, and by extension of human beings. However, Jai Singh did not accept these theories. It is likely that a scholar like him must have heard and read about them. But maybe he didn't want to shake up the status quo, and hence adhered to Ptolemy's belief of a geocentric world.
For centuries, there was an increasing disconnect between what was being observed and what would have been predicted coming from classical Siddhantic kind of calculations in positional astronomy. So, this increasing disconnect actually bothered Jai Singh, and that is how he went about building these gigantic observatories as a means of determining the positions of celestial objects, sun, moon, planets, stars at a given time, contemporary time for him, and using that as the basis, and then thereby being able to calculate the future positions of these celestial objects and use that for calendrical purposes. And his second purpose was to make these accessible to people, to build these in public spaces, to allow people to come, anyone to come and take their own observations, understand how astronomers make these observations, take their own observations and satisfy themselves that this is how they do. But basically they were pure position astronomy measuring instruments built on gigantic scales.
Arjun reaches the stunning Jantar Mantar in Jaipur. This is the largest and the best preserved of all the observatories. There are 16 different instruments here, all in reasonable working condition. All these were made of stone and masonry. This was because this was the material that was readily available in areas around. Though during Jai Singh's time, brass instruments were largely used for astronomy. When Jai Singh designed the observatories, one of his foremost objectives was to create astronomical instruments that would be more accurate and permanent than other instruments in use at the time. His solution was both simple and remarkable. He decided to make them large, really large. This led to the development of a collection of large-scale structures for the measurement of celestial movement that is unequaled even today. Arjun first wanders up to the enormous Samrat Yantra, sometimes called the supreme instrument. This is basically a giant equatorial sundial. Although it is not too different from other ancient sundials from around the world, the Samrat Yantra is important because it measures time to a precision that had never before been achieved. It is capable of measuring time to an accuracy of 2 seconds. Before exploring this instrument, let's take a quick look at the principles that powers a sundial. A sundial, very simply, casts a shadow based on the position of the sun in the sky. A basic sundial consists of a thin rod called the gnomon, which casts its shadow on a dial plate, which is marked with R lines. As the Earth rotates and the sun appears to move across the sky, the shadow cast by the gnomon moves from the dial plate, indicating the time. But it's not so simple. As a result of the tilt of the Earth's axis, the visible movement of the sun changes daily. The curvature of the Earth creates another problem for the sundial watcher. The angle relative to the sun of a stick perpendicular to the surface will be different for various latitudes. This means that every hour's passing will move a shadow more or less depending on its geographic position. So how can the sundial cope with these variations? One way is by keeping the base platform steady, while the gnomon is moved to reflect the changes due to the Earth's axis tilt. Another method achieves the same effect by aligning the platform with the latitude and the gnomon perpendicular. Mathematically, this is just the projection of the gnomon onto the platform. Let us see how Jai Singh's enormous sundial works here. The essential parts of the Samrat Yantra are the gnomon, which is very simply a triangular wall with its hypotenuse parallel to Earth's axis. The base of this right-angled triangle is 44 meters, while the hypotenuse makes an angle of 27 degrees, which is the latitude of Jaipur, and rises to a height of 27 meters. The gnomon has niches in its wall, so storms do not affect the instrument. The yantra also has a pair of quadrants on either side, lying parallel to the plane of the equator. Each of the quadrants is of 15 meters radius. The edge of the quadrants is graduated in hours, minutes and seconds. On a clear day, as the sun passes from east to west, the shadow of the gnomon falls on the scale of the quadrant, indicating local time. The shadow travels about 4 meters in 1 hour. The same shadow moves 6 centimeters per minute. Each minute is further subdivided into 30 fractions, each standing for an incredible precision of 2 seconds. And so, the motion of the gnomon's shadow becomes a palpable experience of Earth's cosmic motion. Arjun then walks across to explore a smaller version of the Samrat Yantra. This is made of red sandstone and white marble. This is similar to the big Samrat Yantra, but here the triangular wall is placed exactly in the north-south direction. The shadow of the triangular wall moves equal distances in equal time intervals on the quadrants. This movement is calibrated to read the local time. Each quadrant is divided into 6 divisions of 1 hour each. These 1 hour divisions are further subdivided in 4 subdivisions of 15 minutes each. The 15-minute segments are further split into 3 divisions of 5 minutes. These 5 minutes are then in turn subdivided into 5 divisions of 1 minute. For more precision, the 1-minute divisions are subdivided into 3 divisions of 20 seconds each. As a result, the small Samrat Yantra gives us a time accuracy of 20 seconds. There are other sundials in the complex. Arjun walks around and takes a quick look. First up, the Nadivalaya Yantra. It is an equatorial sundial measuring solar time at Jaipur. In an equatorial sundial, the dial plate is fixed in the plane of the equator. The gnomon is perpendicular to the dial plate. The hour lines are spaced equally at 15-degree intervals. In this sundial, there's actually a pair of instruments, one facing south and the other north. The former is used when the sun is in the southern hemisphere from the 24th of September to the 20th of March, and the latter when the sun is in the northern hemisphere from the 20th of March to the 22nd of September. The wall of the plates is inclined towards the south at such an angle that the instrument remains parallel to the plane of the Earth's equator. The central iron pinpoints to the pole. At noon, the sun falls on the north-south line. Before noon, the shadow will lie to the west, and after noon to the east. The time is read in the normal way. Arjun then heads off to the Ram Yantra. This structure consists of a pair of massive cylindrical structures open to the sky, each with a pillar or pole at the center. It has 12 vertical columns and horizontal slabs. The pillars are of equal height, which is equal to the radius of the structure. The structure represents a celestial sphere in an inverted form, horizon on the top and the zenith on the bottom. So what do we mean by altitude and azimuth? Azimuth and altitude are two coordinates that define the position of a celestial body in the sky as viewed from a particular location at a particular time. The altitude is the distance an object appears to be above the horizon. The angle is measured up from the closest point on the horizon. The azimuth of an object is the angular distance along the horizon to the location of the object. By convention, azimuth is measured from north towards the east along the horizon. It determines the direction of the celestial body. For example, a celestial body due north has an azimuth of 0 degrees, one due east 90 degrees, one due south 180 degrees, and one due west 270 degrees. The Ram Yantra is inscribed with 360 vertical lines representing the azimuth circles and 90 horizontal lines or altitude circles. The Rama Yantra is used to observe the position of any celestial object by aligning an object in the sky with both the top of the central pillar and the point on the floor or wall that completes the alignment. In the daytime, the sun's position is directly observed at the point where the shadow of the top of the pillar falls on the floor or wall. At night, an observer aligns the star or planet with the top of the pillar and interpolates the point on floor or wall that completes the alignment through the use of a sighting guide. The floor is constructed as a raised platform at chest height and is arranged in multiple sectors with open spaces between them. This provides a space for the observer to move about and comfortably sight upwards from the inscribed surface. The instrument gives direct readings and is most accurate near the intersection of floor and wall, corresponding to an altitude of 45 degrees. Here the markings are at their widest spacing and give an accuracy of ±1 degree of arc. For altitude readings greater than 45 degrees, the accuracy diminishes to ±1 degree near the base of the pillar. The Jaipur Jantar Mantar houses one of the largest astrolabes in the world. An astrolabe is a medieval instrument for the measurement of time and the position of celestial objects. Astrolabes are used to show how the sky looks at a specific place at a given time. This is done by drawing the sky on the face of the astrolabe and marking it so the positions in the sky are easy to find. To use an astrolabe, you adjust the movable components to a specific date and time. Once set, much of the sky, both visible and invisible, is represented on the face of the instrument. This allows a great many astronomical problems to be solved in a very visual way. Curious to see how this version of the astrolabe works, Arjun walks up to the enormous Yantra Raj. This one is 3 meters tall and almost 400 kg in weight. This is a map of the visible portions of the celestial sphere, which can be used to calculate a vast amount of astronomical data. The hole in the center of the instrument is the position of the pole star. By placing a separate disc in the hole, which is graduated from 0 degree to 180 degree of instrument, we can calculate the positions of various planets, and by dividing by time interval, the speed of rotation of a particular planet is calculated, and with this, the dates of sun and moon eclipses as well as the sunset, sunrise, moon set, etc. are calculated. The back of the yantra is fitted with a bar used for sighting. The plain disc to the left is intended for use as a blackboard to record observations and calculations as they are made. We can only see the sun during the day, and the stars only shine at night. What if we could see everything, the sun, moon, planets and stars, during the daytime? This is the basic idea behind Kapali Yantra, and indeed behind most observational astronomy before the invention of the telescope. The Kapali Yantra consists of 2 sunken hemispheres. Their horizons are calibrated from 0 to 90 degrees and from 90 to 180 degrees. These instruments display the complete structure of the sky and the movement of the stars around the Earth. A map of the heavens is engraved on each bowl, showing the positions and motions of various heavenly bodies throughout the year. Two wires are arranged to cross above the surface of the bowl. The shadow of their intersection gives the position of the sun projected onto the celestial map engraved in the bowl. This allows the observer to determine the position of the sun relative to the planets and zodiac at any time of the year, for use in horoscopy and other astronomical calculations. Arjun next walks across to check out the kaleidoscopic, the Jai Prakash, which may well be Jai Singh's most elaborate and complex instrument. This was built last, and with the help of this instrument, the readings and calculations of the other instruments could be verified or rectified. The Jai Prakash has two cavities, each about 5.5 meters in diameter. These cavities represent halves of the Earth. The interior surface is divided into 6 marble slabs, each further divided into minutes and seconds. A map of visible heavens is inscribed on the inner surface of the bowls with additional scales, including the zodiacal divisions of the year around the rim. A taut cross wire suspended at the level of the rim holds a metal plate with circular opening directly over the center of the bowl. This plate serves as a sighting device for night observations and casts an easily identifiable shadow on the interior surface of the bowl for solar observation. The surfaces of the Jai Prakash are engraved with markings corresponding to an inverted view of both the azimuth altitude or horizon and the equatorial coordinate systems used to describe the position of celestial objects. So much to see and explore, and all in one space. Astounding to see ancient instruments that still work so scientifically and accurately. Architecture used for science. Science used for architecture. This structure still stands testament to the overwhelming scientific innovation that powered India.